This is the subset of my original dataset, and these are first couple of images generated by the generator, and you can see how generators start creating the features in these images. And now these are some last couple of images where I have ran my network for 4600 epochs, and it has started creating this kind of images. And these are my final outcome where I have saved 100 images after 4600 iteration. Hello mates, this is the Unemployed Geek. Welcome back to my YouTube channel, and today I am going to discuss about how we could make or generate more image data by using a set of image data of a particular object. Basically, today I am going to cover Generative Adversarial Networks or GAN, which was introduced for the first time by Goodfellow, which was a vanilla GAN in the year 2014. And I will cover how these GAN networks work, how they generate images, and how discriminator helps them creating more prominent feature or more fine features in the synthetic data or the input. So today I am going to talk about deep convolutional GAN or DCGAN. I have chose this model as it will be easier to understand the architecture of generative AI or GAN networks, how this model works. So please try to not skip this video as I am going to share small and important fundamentals in this video. So let's dive in. Now let's understand the architecture of the GAN networks. So have a look at this image. We could easily find out that there are two main components. One is generator and another is discriminator. So before that, we need to understand what is latent space and what is latent vector. So we will be needing latent vector, and latent vector is a vector which will be placed in a multi-dimensional space, which is latent space. And this latent vector will help the generator to generate fake samples. Then these fake samples will go to the discriminator along with the real samples. Here inside the discriminator will try to find out either the generated samples are real or fake. Basically, it used to calculate the loss. It used to calculate the difference between the real samples and the generated fake samples. Once it understood the difference between fake samples and real samples, it will again come to generator, and generator will again create another set of sample by tweaking the latent vector, by changing the values of the latent vector. And this process will continue until and unless generator will be able to create the samples which discriminator cannot discriminate. Either it is a fake sample or a real sample. That means the loss will be minimal at that place. So this is the basic concept behind it, and I have ran my network for 4600 epochs. After that, it used to produce this kind of images. So now let's dive into the coding part. As I have already told earlier in this video that I'm going to use DCGAN or deep convolutional GAN. That means this model is inspired from convolutional networks or CNNs. I will discuss about CNN in my later videos, so please stay tuned, keep supporting, and if you are new to this channel, please do subscribe. So let's have a look on the file structure of my directory. So here in this directory data, I have kept my sample data which I'm going to use for training, and let's activate the virtual environment. So I'm using Python virtual environments. So if you want to know how we could create the virtual environments in Python, so you could definitely follow my previous videos. So I will drop the link in the description, so you could definitely give it a watch, and you could install the libraries inside that, how you could use that virtual environment inside the VS Code. I have explained all those things in that video, so I will put the link in the description. So I'm going to use two main libraries here. One is torch and another is torchvision. So you could install them by using pip install. I have already installed them. Let's create an empty file where I will derive the network. So let's name it as gan underscore net.py, and let's edit this empty file in VS Code. So as you can see, this has created the empty file root directory, and let's import the libraries. So here I'm importing torch because I'm going to use NN module from torch, which will help me to create the network. So first of all, let me create the constructor for the discriminator. So I'm declaring it as super because I want to use all its functionalities, all its attributes. And let's add the first convolution layer. Convolution layer is done. Now I have to put the activation function leaky relu 0. That's it. Now let's understand how it will work. So as I told you, like, I will discuss about CNN in my later video, but still I could, if I could show you how this convolutional model will work mathematically, or what will be the output after one layer, then it could be easier to understand. So let's copy the first convolution layer of the discriminator and let's break it down. Let's paste it over here, and then let's have a look on the arguments which were parsing in that convolution. First is input channel NC, the value is 3, and then output channel, which is NDF divided by 2. NDF is basically the size of my feature vector of discriminator, which is 64 128 divided by 2. Then my kernel size is 4, then stride is 2, and then padding is 1. Now let's calculate the output of this convolution layer. The formula of calculating the output is input size minus kernel size plus 2 into padding divided by stride plus 1. Let's put those values one by one. Input size I am taking as 128 minus 4 plus 2 into padding is 1 divided by stride is 2 plus 1. What I am getting? 126 divided by 2 plus 1. So 63 plus 1, it is 64. So after convoluting over the input of a 128 cross 128, I am getting 64. Then again in the next layer I am getting 32. After that I am getting 16. After that I am getting 8, and at last I am getting 4. That means my output after every layer getting shrinked. Okay, let's paste the other layers as well, and let's edit the arguments for this convolution layers as well. Here this will be my input channel and output channel will be NDF, and number of size of kernel will be 4, and stride is 2, and padding is 1. After this convolution layer, I will add another normalization. It will be a batch normalization technique. So batch norm 2D and NDF. So that means I'm normalizing the output from my second convolution layer. Then I have applied activation function, and here I am going to use sigmoid. So now I have to add a forward pass for it. So here by doing this I am done with the discriminator network, and then let's go for the generator network. So let's define another constructor, name it as generator, and again I am declaring it as super. And let's add the first deconvolution layer. Have to put a batch normalization here. Now the activation function relu true. So now let's understand how this generator will work in the perspective of the output of the deconvolution layer, like we have seen for the discriminator. So let's copy the first layer of the generator and I'm pasting it over here so that I could describe the thing. Now look at the arguments. First argument is the input channel, which will be my latent vector, and second argument is my output channel. NGF is the size of the feature vector of my generator, multiply by 8, which is 128 multiplied by 8 equals to 1024. Now then kernel size is 4, stride is 1, and padding is 0, and bias is false. Now let's calculate the output for this deconvolution layer. Now there is a formula of calculating the output as well. that is input minus 1 multiplied by stride minus 2 into padding plus kernel. Let's put the values over here. So I'm assuming that my input will be 4 cross 4. So input minus 1 means 4 minus 1 multiplied by stride is 1 minus 2 into padding is 0 plus kernel size is 4. Now what I'm getting? 3 plus 4, which is 7. So in the next layer I will get 14. After that I will get 28. After that I will get 56. Then 112. Then 224. That means after every deconvolution layer, my input is increasing. Size of my input is getting increased. That means it is generating the image. Let's copy this part and paste it over here. Now let's do the changes here. So this is my first layer where my input is my latent vector and output is 128 into 8, and in my next layer this will be my input and my output will be ngf multiplied by 4, kernel size is 4 and stride is 2 and padding will be 1. Then batch normalization will be 4 as well, and then ReLU. Finally, this will be my last layer. Here the input will be ngf divided by 2 and my output layer will be my number of channel and kernel size will be 4 and stride is 2 and padding will be 1. And here batch normalization we won't be needing, so remove that, and the activation we will use here in the last layer, that is tan h. That's all. I have to put a forward pass here, so let's define the forward pass. So we will be needing a forward pass here, so let's define a forward pass. Forward self and input return self dot main input. So after doing this, we are done with the model part. Now we have to train the model. So let's write another script to train the model. So let's name it as, let's open this and let's start editing this one. So again, for this we need to import the necessary libraries. So let's import them one by one. Import OS to perform OS related or system related file handling or this kind of work. Okay, this kind of task we need to perform, then we will use this OS, like create the directories or create the files. So for doing such kind of operations we will be needing this OS library. Then import torch, then import arc parsers, because I want to give the command line argument to run the epochs, to define the number of epochs. That is why I'm using arc parser. Import torch dot optimizers as optim. This will import the optimizers. This will import the optimizers from the torch library. Then import torchvision dot utils as vutils. Import torchvision dot datasets as dsets. So this dataset actually will help to create the dataset from torch dot utils dot data. Import data loader. So this data loader will help to load the data, and this data sets will help to create the data set. Import torchvision dot transforms as transforms. Finally, we have to import our network file, which is DCGAN model. DCGAN model. Import the generator and the discriminator. Okay. So now once we are done with this, let's define a function which will train my model. Okay, which will train my model on those data sets. Okay, so let's do it. Train net discriminator network generator network, then latent vector, then number of epochs, then data loader, then device, then criterion, then discriminator optimizers, then generator optimizers, then epoch dir. This directory will actually store, this epoch dir will store the images after every epoch. Okay, so now we have to define the noise first. This will create the noise which will be given to the generator to generate new image. So as you can see, this noise is taking latent vector. Okay, so now for epoch in range of number of epochs and for I comma data in enumerate data loader and 0. Now we have to update the discriminator. First we have to make the gradients as 0. So let's do it. Dot 0 grad. Then process the real images batch size equals to real image dot size of 0. Label. So I'm smoothing my labels by using 0.9 here instead of using 1, making it binary to avoid the overfitting, because already I have faced that problem. So after that I have decided to smoothen the real levels. Data type equals to torch dot float and device equals to device. Now after this I have to calculate the loss. So let's get the output first. Output equals to the loss for the discriminator. We have to calculate criterion output and so it will generate me the loss. Then now I have to generate some fake images. So that is why again I need to create the noise. Let's generate the fake image. We have to again smoothing the labels for fake images. So let's do it. So there I have used 0.9. So I have to use here 0.1. Let's find out the loss the discriminator loss for the fake images. Now, after this point, we just have to update the discriminator weight. So we have updated the discriminator weights as well. So now let's do the same for the generator as well. So let's reset the gradient to 0. Let's calculate the loss for the generator. Update the weight for generator. So now let's print the status of the training in our console. So by doing this, we could print, or we could look after every epoch on the console. So let's save the images after every epoch. Return generator network and a discriminator network. Well, so let's define a main function where we will parse all the variables, or we will assign all the variables, and we will call this function inside that main function. Let's do it. Parser equals to arg parser dot parser. Leave the directory first. So model dir, where I will store my trained models, equals to saved models. Epoch images will be epoch images. Epoch images, and data directory will be data. Now maybe sometime what happens, this image file may not be available, so we have to create them manually. So to do that, os dot make dirs and model dir exist. Okay, true. So if it is exist, it will not create anything, and if it is not exist, then it will create that particular directory. Declare the hyperparameters. So batch size will be 128, then image size will be 128, then latent vector will be 100, then feature map for generator ngf will be 128, and feature vector for discriminator will be ndf, it is 128, and then number of channel will be 3. Now number of epoch, which I will take from command line, so that will be args.e args.a args.e, then learning rate for the generator, learning rate for the discriminator, which is 0.0004, and beta 1, which will be needing in optimizer. For Adam optimizer, we will be needing this beta parameter, which will be 0.5. Now then define the device equals to torch dot device and CUDA if torch dot CUDA dot is available. Else CPU. Okay, so that means if my GPU is available, then it will use GPU. If there is no graphics card or GPU in my system, then it will go with the CPU. Okay, then let's transform the data which I have to load for training. dot resize image size, comma, transforms dot center crop image size, comma, transforms dot to tensor. Now transform dot normalize 0.5 comma 0.5 comma 0.5. So it will normalize and transform my data to a tensor. So now let's load this data. So now this will load the data into the data loader, then initialize the generator and the discriminator network from the model file. Now let's define the loss function and the optimizers. Let's call that training function here. Now generator network comma discriminator network equals to the arguments will be discriminator network comma generator network comma latent vector comma number of epochs and the epoch dir, which is epoch images. So it will now train my model, and let's save the generator network and the discriminator. Sorry, let's save the generator model and the discriminator model after the training. So for do that, torch dot save generator network dot state dict comma os dot path dot join of model dir comma and the file name generator.pth and torch dot save discriminator network dot state dict now if name equals to main, then main. So here I'm done with the training script. Let's run it for 10 epoch and let's see if it is working. So it's giving an error. Hopefully it will work well. Okay. Great. That's it for today. Thank you for watching. We will again come back with our next video, and bye bye till then. Keep supporting, keep watching, and please do like, share and subscribe. Bye bye.